It's Mrs. O'Gorman again, and today we're going to be tackling a big topic, and I'd like everyone to get ready with what they need. So you should have your notes pack, and you should have it open to page 21, and you should definitely have a pencil and some colored pencils or a highlighter or colored pens or something because we're going to be marking up some diagrams. So today we are going to talk about wave speed, the speed of PNS waves in the Earth, and the essential question on page 21 is, what do seismic waves and seismograms tell us about Earth's interior structure? This is a big ticket item, folks, so pay attention. By now, you should have watched many videos. Your assignment over the last day was to watch a lot of videos, tutorial videos about seismographs, about PNS waves, about their movement, and about what materials they can travel through. And you filled in your PNS wave table, and you should have corrected it by now. The answer key was posted, and hopefully you have that table filled in. So I'm hoping that what I'm about to explain is reiterating what you've already seen, and just putting a little bit of an O'Gorman twist on it. So here we go. So wave speed is determined by the characteristics of the material that the earthquake's wave is moving through. This is true with any waves, right? The speed of a wave is determined by what material it is traveling through. And of course, we know that different materials have different densities. And the rule is that the denser the material, solids are denser than liquids usually, the faster the waves can move through it. But remember, P waves, no matter what material they're moving through, P waves will always move faster than S waves. So here we see an earthquake off the coast of Washington State. Maybe that had to do with the Juan de Fuca plate. And you see the blue going out and the red going out. What do you think the blue is? What kind of waves? You got it, P waves, and the red is S waves. So you can see that they move faster coming off of an earthquake. All right. And remember when we were studying the layers of the earth, page 10, and you asked, hey, if we've never been there, how do we know that these layers exist? Because we've never dug there. We've never ever been there. Here's how. Um, the velocity of the P waves and S waves increase as they travel deeper into the Earth, and this is due to differences in density. And you should have also watched a little video about our friend Mohorovicic. Sal Khan explained to you how he discovered the Mohorovicic layer. I'm going to use cyan today. Um, and that little discontinuity between the crust and mantle is called the moho because scientists didn't want to walk around going, hey, yeah, that layer is called the Mohorovicic discontinuity. They just shortened it up to moho. All right. So, changing densities, changing velocities. Again, this is physics. Waves move at different speeds because of physics. These are rules. All right. So let's take a look at a little animation that shows you about wave refraction. And Sal Khan also explained this to you in his video. So this is wave refraction. Okay, so in this little model, the upper layer is the lower layer is going to move in the lower layer the waves move slower than in the upper layer. So if the waves are going to move slower down here and the waves are going to move faster up here, tell me about this density down here. If the waves move slower, the particles have to go further to transmit the energy, which means this layer is probably, yep, less dense, and this layer is more dense, all right? So if we play, there's the speed, and it's slowing down. The wheels on that side of the car are slowing down first, like Sal was talking about, all right? But let's pick A. The lower layer is going to be faster than the upper layer. So here comes the wave, just like we did in ocean waves. Here comes the wave. And when this part of the wave hits, it's going to speed up, right? And it's going to move faster. So there's the refraction right there. So we can see here that waves do move in different speeds and different materials based on densities. Here's another model. Now this is an actual model that makes it look like the Earth. So the top brown layer might be the lithosphere, and maybe this down here is the asthenosphere. So let's activate it. And there's the speed increase. And this is the MOHO. This is what he discovered, okay? Or though maybe here this is more dense and this is less dense, and that's when the waves slow down. So suffice it to say that waves do change speed as they're traveling through different layers, or different, excuse me, different density layers. Okay, so what does that mean for us? What does that mean for us in terms of earthquake waves? Well, what do we have here? Whoops. Let's go back. I'm trying to stop it. Okay. What waves are these? Let's take a look at this model. Here are S-wave ray paths. And remember that here's the earthquake. And in most of these models, the earthquake is going to be up top. But of course, if this is the Earth, not all earthquakes happen at the North Pole. You have to be able to take this model and rotate it. So what if the earthquake happened over here? What if the earthquake happened there? What if the earthquake happened over here? What if the earthquake happened over here? Well, wherever the earthquake occurs, this pattern will change with it. All right, so maybe this is an earthquake that occurred on Earth, and these are the S waves. Well, why wouldn't any of these stations down here feel that earthquake? Why wouldn't any of these seismograph stations feel that earthquake? Let's say you have a seismologist here, right? He lives here or she lives here, and they're like, oh my gosh, my seismogram, I just felt an earthquake. And they call their nerdy seismologist friend who lives over here. Say, get ready for this earthquake. It's a big one. It's a big one. Your seismograph machine should be shaking any minute now. And they were sitting here waiting and waiting and waiting and waiting and waiting. And they got nothing. They get nothing except for the surface waves, which only go around the surface, right? So why wouldn't they feel an earthquake? Why wouldn't they get any S waves here? Well, it's because there must be something liquid in between this quake and this person. Not only this person down here, but all the seismograph machines, all the seismometers that are down here. This is how we figured out that the outer core is liquid, because S waves were not detected down here. Now, how did we figure out about the inner core and the different densities of the layers? Well, there's that liquid outer core. All right. Well, here's the P waves. Here are the P waves. Hold on. Okay. Now, what if you're a seismologist and your machine is here? Well, not only are you not getting S waves because the liquid outer core is blocking them, but you're not getting any P waves either, because here's what's happening. This P wave here, this P wave that just missed that liquid outer core, that's getting bent. It's getting refracted because of the varying densities of this material. The first P wave that hits this liquid outer core, boy, is it going to refract big time, because it's going from a solid to a liquid. So look at this refraction, right? It's going to refract in that liquid outer core, and then it's going to meet the core mantle boundary here, and it's going to refract big time again, right? So all of this refraction of these P waves between the P wave that just missed that liquid outer core and the P waves that hit this liquid outer core create what's called the P wave shadow zone. All right, so the S wave shadow zone is one huge side of Earth. The P wave shadow zone, I know this is hard to see because it's two-dimensional, but it's like a ginormous donut on the Earth. All right, so let's take a look at what the varying seismograph stations will see. Okay, so a seismograph station that is not in any shadow zone is going to get P, S, and L waves, surface waves. A seismograph station that's in the P and S wave shadow zone is only going to get those surface waves. And a seismograph machine that's down here on pretty much the opposite side of the Earth from where the earthquake was is going to get P waves, no S waves, and surface waves. All right, so that's a nice model there. Let's watch it one more time together. That's how we discovered the liquid outer core. That's what Inga Lehman did. All right, Inga Lehman, if you watch the Bill Nye video on my feed, you're going to see how she discovered this. Go seismologists, go girls. Okay. So, there's nice animations here. I did get them to work on my Mac, and if you would like help with that, I can maybe help you with that if you want to get these animations in the PDF to work. Now, you may be asking yourself why. Hey, Ms. O'Gorman, why can't S waves go through liquids? And here's an explanation. It's due to the strength of materials. I want to show you a nice molecular view. This is a molecular model. So these are molecules or atoms of material. And this is a solid because it has a crystalline structure here. I want to show you how a P wave transfers energy. Molecule to molecule. Boom, boom, boom. They're pushing one another. all right? They're able to do that. But an S wave is a shear wave. It rips the material, okay? It rips the material. I'm going to play that one more time, okay? It rips it. So you have to have these molecular bonds here, these strong bonds that a solid has. In a liquid, are molecules able to push one another? Yes, because liquids, um, you can squeeze them. Okay, you can squeeze them. Gases, okay, a molecule hits a molecule, it can hit them. However, if you tried to use a scissor to cut water, would it cut water? If you tried to use a scissor, a shear, to cut air, would it cut air? No, because solids are the only ones that have shear strength. Liquids and gases have no resistance to shearing motion. All right. So that's why liquids and gases cannot transmit shear waves. All right, let's go back to the PowerPoint because I want you to uh, do something right now as an activity. Okay. These are all pictures. Okay, this shows you the MOHO here, the MOHO discontinuity. Okay, there's the MOHO right there. All right. This shows you the varying speeds of waves as they travel through the Earth. CMB, by the way, CMB stands for core, mantle, boundary. All right. This shows you the sudden decrease in speed as the P wave goes from the solid mantle to the liquid outer core, and the sudden increase of speed as the P waves go from the liquid outer core to the solid inner core. And here you can just see, bam, S waves just stop because they cannot travel through liquids. All right. So all these notes explain what's going on. All these notes explain what I was just explaining to you. Now this next page I like. We're at the top of page 25. This one I like because it kind of shows you the three-dimensional view of the shadow zones. So this entire side of Earth, this entire side of Earth, that's going to be the S wave shadow zone. But let me change the color. Pen color, let's go to green. Okay. But this donut area in here, okay, this donut looking area in here and this donut looking area in here, that's the P wave shadow zone in here. Okay, so it goes like a donut around the Earth, and then the P waves do get through to here. So here's what we're going to do. Let's say we sent a rover to another planet, and the rover was able to make waves. The rover was able to make seismic waves. Okay, the directions for the bottom slide on page 25 say use the S wave shadow zones shown to infer and draw the size of the liquid core in planets A and B shown. So if any core has a liquid, if any planet has a liquid core, and we send a rover there, and the rover goes boom and makes seismic waves. It has this big like pounder thing, and it makes seismic waves on the planet. And then we have sensors around the planet, and the sensors were like, oh, all of these sensors, none of these sensors in this area received any S waves. Could we then infer the planet A's liquid core? If we made seismic waves here, like we send a rover, boom, and make boom, it shakes the planet, right? And we have other seismographs all around the planet, seismometers all around the planet. And the only seismometers not to receive S waves were here. Could we infer this planet's liquid core? The answer is yes. So I would like you to pause the video right now, and I would like you to draw the liquid outer core. Just draw a circle best you can using this pattern. Draw a circle that would represent the liquid outer core of planet A and planet B, please. Okay, so we're back, and you should have done something like this. You should have drawn like an arced pattern here and an arced pattern here. And then that would make you think that the liquid outer core would be about that. This is going to be a really bad circle, folks. About that big. Oh, that's really sad. Okay. And then planet B, if you follow this pattern of the refraction of the S waves, let's see. It's hard to do on a trackpad. You know that? It would be like that, maybe. And like that, maybe. Oh, this is really bad. I'm sorry. And then the liquid outer core here would be smaller, right? There's something like that. All right, so hopefully you guys did better in your notes pack than I did on my trackpad. All right, here's on the next page, on page 26, here's a nice diagram of the P wave and S wave shadow zone. And the next one is a nice color. Also, it's a little better because it has the oblique view of the side of the Earth over here. So I hope this helps with P wave and S wave shadow zones. Again, this is how the question was: how do we know the interior structure of Earth if we've never been there? And the takeaway is, hey, the way we know the interior structure of Earth is because seismologists and geologists have been studying seismic waves, analyzing them, and using the properties of materials and the scientific properties of wave action to determine Earth's interior. We were able to determine where the boundaries between the layers are. We were able to estimate the densities of the materials. And this is all because of scientific principles of waves. That's how we've done it. All right. So, no, we've never been there, but we have figured out what's there. And remember, on page 10 is called the inferred properties of Earth's interior. We inferred them based on prior knowledge and scientific principles that have been proven. So, everyone, now what you're going to do is you're going to answer the questions on page 27, and you are going to enter them into the form on Teams. Okay, so I uploaded a form to Teams, and you're going to enter your answers on there, A, B, C, D, or E, for questions 13 through 22, and it will auto correct it. All right, take care, everyone. Bye.